If you own or manage a parking lot, you already know two things that drive you crazy. During the day, the cars sitting out there turn into ovens. People open their doors and get hit with that wave of hot air. The interior gets damaged faster, the batteries take a beating, and nobody's happy walking back to a car that's been baking in the sun for hours. Then at night, that same parking lot starts costing you real money. The lights have to stay on for safety and security. The cameras need power. And every month, you're paying the electric bill for something that should honestly be free, especially when you have all this open space sitting under the sun all day. That's the problem I wanted to solve. I didn't just want to put some solar panels somewhere. I wanted to build something that could do two jobs at the same time. Give the cars real shade during the hottest part of the day, and then use that same sunlight to power the lights, cameras, and even phone charging stations at night without increasing my electric bill by a single dollar. Most people think of solar as something you put on a roof, but what if you turn the parking lot itself into the power source? That idea is what made me decide to build a solar parking lot canopy. A proper structure with solar panels on top that works as both shade and a power plant. So I stopped complaining about the heat and the bills, and I actually went ahead and built it. Here's what I used to make it happen. I used regular solar panels, the kind you can buy pretty easily. I built a strong metal frame that could hold those panels above the parking spaces like a big canopy. Underneath, I installed a battery bank so the energy collected during the day could be stored and used later. I added a charge controller to keep everything safe, an inverter so I could run normal lights and devices, some bright LED lights, and a couple of security cameras. The goal was simple: make the parking lot shade the cars by day, and then power itself at night. At first, I wasn't even sure it would work properly. I had a lot of doubts. Would the batteries actually last through the night? Would the lights be bright enough for security? Would the cameras keep running without me having to plug anything into the wall? But instead of jumping straight into the build, I want to show you something more important. First, the real difference this kind of solar canopy can actually make for a parking lot. Because once you see how much it can reduce heat during the day and how much power it can generate for free at night, you'll understand why more and more people are starting to look at their parking lots in a completely different way. Once I had all the materials on site, I started building the frame. The canopy I designed was 40 feet long and 24 feet wide, big enough to cover 6 standard parking spaces. I used 4x 4-inch square steel tubing with 0.083-inch wall thickness for the 6 vertical posts, and 2x 4-inch rectangular tubing for the horizontal beams and purlins. All steel was 1/4 gauge, thick enough to handle wind but still workable. The first real step was setting the posts. I dug 6 holes, each 36 inches deep and about 20 inches wide. At the bottom of each hole, I put a 1-2-inch layer of gravel for drainage, then poured 3,000 pounds per square inches concrete with 2 pieces of #4 rebar inside for strength. I embedded 3/4-inch galvanized anchor bolts into the wet concrete using a wooden template so everything would line up. After pouring, I braced each post with temporary 2x4 lumber and checked them with a 4-foot level on 2 sides. I let the concrete cure for 2 full days before moving on. Once the posts were solid, I started assembling the main frame on top. I cut the horizontal beams to length and bolted them to the posts using 1/2-inch grade 8 galvanized bolts with lock washers. I chose bolting instead of welding so I could adjust or take things apart later if needed. For the roof, I added purlins every 4 feet across the beams to give the solar panels solid support underneath. Mounting the solar panels turned out to be more difficult than I expected. Each 400W panel is about 6.5 feet tall and weighs around 50 pounds. I installed aluminum solar rails on the purlins, then used mid-clamps and end clamps to secure the panels. Because it was often windy, I always worked with at least one other person. One held the panels steady, while the other tightened the clamps to the recommended 12-15 Nm torque. I also left about 6 inches of space between each panel so wind could pass through and reduce pressure on the structure. One problem I didn't plan for well enough at the beginning was leveling. The parking lot has a slight slope for drainage. After setting the first few posts, I noticed some were up to 3/4 inch higher than others. I had to go back and make steel shims from 1/8 inch and 1/4 inch flat bar. Then place them under the base plates until the entire top frame was level within about 1 inch across all 40 feet. If I had skipped this, the panels would have sat uneven and created long-term stress on the frame. I also added diagonal bracing, using 2x2-inch square tubing on the sides, most exposed to wind. This helped make the whole structure much more rigid. I made sure every bolt was properly tightened and used lock washers so nothing would loosen over time from vibration or wind. I also paid attention to electrical bonding and grounding. Even though the full electrical work would come later, I ran a continuous #6 bare copper grounding wire along the entire metal frame and bonded all the posts and rails together. This is an important safety requirement and helps meet electrical code in case of a lightning strike or any fault. By the time the frame was finished and all 12 solar panels were mounted and secured, the parking lot already looked completely different. You could clearly see the large shaded area it created during the day. But even with the structure done, one big question was still on my mind. Once the sun goes down, would the batteries actually store enough power to run the lights and cameras through the entire night? That was the next thing I needed to find out. With the canopy frame and solar panels finished, it was time to deal with the electrical side. This was the part that made me the most nervous because everything depended on whether the system could actually store and deliver power at night. I decided to use a 48V system because it's more efficient for longer wire runs and reduces power loss. I installed 4 12V200 lithium iron phosphate LiFePO 4 batteries wired in series to make a 48V200 battery bank. This gave me roughly 9.6 kilowatt hours of usable capacity, which I calculated should be enough to run the lights and cameras through the night with some reserve. For the charge controller, I used a 60A MPPT controller. It's more efficient than PWM controllers, especially when the weather isn't perfect. I set the charging parameters according to the battery manufacturer's recommendations. Bulk charge at 56, 8V, absorption at 56, 8V for 30 minutes, and float at 54V. I also installed a battery management system, BMS, that came with the batteries to protect against overcharging, over-discharging, and high temperatures. For the inverter, I chose a 3000-watt pure sine wave inverter. This was oversized for my needs, but I wanted headroom in case I added more loads later. I mounted it on the wall inside a small weatherproof enclosure, along with the charge controller and circuit breakers. Wiring was another important part. I used 2/0 AWG copper cable for the main battery connections to minimize voltage drop, and 6 AWG for the solar panel strings going to the charge controller. All positive lines had appropriate fuses or circuit breakers, 125A on the battery side and 60A on the solar input. I also installed a shunt and a battery monitor so I could see exactly how much power was going in and out in real time. When I first turned everything on, I did a test discharge. I connected the lights and cameras and let the system run overnight with no sun the next day. By morning, the batteries were down to about 35% state of charge. That was lower than I wanted. It meant my original calculation was a bit optimistic, probably because I underestimated the power consumption of the cameras and the inverter's idle draw. I had two choices: add more batteries or reduce the load. I decided to add 2 more 12V200 batteries, bringing the total bank to 48V300 about 14.4 kilowatt hours usable. I also lowered the brightness on some of the LED lights and set the cameras to record only when motion was detected instead of running continuously. After these changes, I did another test. This time, the batteries only dropped to 62% by morning, much better. I also added proper ventilation for the battery enclosure and made sure all connections were tight and protected from weather. Safety was important to me, so I labeled every wire and installed clear signage on the enclosure. By the time I finished the electrical work and did the final adjustments, I felt much more confident. The system was now set up to handle a full night of lighting and camera operation with a comfortable reserve. But the real test was still coming. The first actual night after a full day of sun, when everything had to work automatically without me babysitting it. That test is what I'll show you next. After weeks of planning, building, and adjusting, the day finally came for the real test. It was a clear, sunny day, perfect conditions. The solar panels had been producing power all day, and the batteries were fully charged by late afternoon. I turned off all the lights manually in the evening and waited to see what would happen when it got dark. As the sun started to set, I stood in the parking lot and watched. When it became dark enough, the lights turned on automatically. There was no switch flipped, no timer I had to set that night. The system just did its job. The LED lights came on steadily across the canopy, lighting up the parking spaces clearly. The security cameras powered up and started recording without any issue. I checked the battery monitor. Even after running the lights and cameras for several hours, the batteries were still at a healthy level. By the next morning, after a full night of operation, the batteries were at 58% state of charge. That was well within the safe range, and it meant the system had more than enough capacity to handle cloudy days as well. What surprised me most was how natural it felt. I walked around the lot at night, and it no longer felt dark or unsafe. The cars parked underneath were protected from the sun during the day, and at night the whole area had reliable lighting without me paying extra on the electric bill. I even tested the USB charging station I had added. It charged phones normally, powered completely by the solar energy collected earlier that day. Looking back, there were definitely things I would do differently if I built another one. I would have calculated the load more accurately from the start, instead of having to add batteries later. I also learned how important proper grounding and good wire sizing are for long-term reliability. But overall, the project turned out better than I expected. The biggest lesson for me was that you don't need a massive, complicated system to get real results. This canopy now does two useful things every single day. It shades the cars when it's hot, and it provides free electricity for lighting and security when it's dark. That combination made the whole effort worth it. If you have a parking lot, a large driveway, or even just some open space, you can start smaller than this. You don't have to cover 6 parking spaces on your first try. Even a smaller version can give you shade and some free power. The important things are to plan your loads carefully, use quality components, follow safety rules, and be willing to adjust as you go. For me, seeing the lights come on by themselves that first night was the moment it all felt real. The parking lot was no longer just a place to park cars. It had become something that actually worked for me. Thank you so much for watching this video all the way to the end. I really appreciate you taking the time to follow along with this project. If you enjoyed it, please consider giving it a like and subscribing so you don't miss future builds. I'll see you in the next one.